Welcome to this presentation. I'm going to be talking about Nillion, what it is, what it does, and how it compares against blockchain technology. I'm going to leave another question aside for another presentation, which is how Nillion works, actually, the mathematics behind it, because it deserves its own presentation. But let's now focus on the nature of the beast and see what it does and how it compares to blockchain technology. In the last few years, there's been a lot going on in the blockchain space. And one comes to think that actually blockchains would be the same as decentralization. Those two concepts would be the same. But what if it's not the case? What if blockchains were just the tip of the iceberg and there was so much more to come to the decentralized space? At Nillion, we think that that is actually the case. And to illustrate this point, let me just walk you through a brief history of the internet. Back in the 90s, we had the first version, Web 1, which was primarily static. And so it was very limited in terms of the privacy preserving mechanisms that you could implement. And therefore, a large chunk of the web back then was public. But then along came Web 2, and with a much better ability to run complex logic in the browsers, and that enabled the implementation of complex privacy-preserving mechanisms supporting things like secure authentication or strong authentication and all forms of secure payments. In fact, this property, which is confidentiality, the ability to hide information from one another, one could argue that has been fundamental to the growth of Web 2. You can almost not think of anything, of an application in Web 2 that doesn't make use of confidentiality. So Web 2 is great, but it has a problem. It is centralized. And for those of you in the space, in the decentralized space, know what this means. It means that you have to implicitly trust the service provider. They have full control over the service that they are provisioning to you. This may seem okay, but it's actually not okay if you think forward at what's coming next in this century. I think we've all seen what artificial intelligence can do, and it's not hard to imagine that very soon a lot of decisions will be automated in some way or form. So I'm talking about medical diagnosis, court rulings, medical prescriptions, or maybe identity verification. A large chunk of our lives in some way or form is going to be automated, and also those from companies and governments. So one question, of course, is about the ethics of that, of automating all of that. But there's another equally important question, which is around the type of infrastructure that we want to actually run all those automated processes on top of. And it better not be Web 2, because Web 2 is flawed in a number of ways. It's not fully fault tolerant, and even the best companies out there struggle with security. That's why Web 3 positions itself as a very interesting alternative, because it has two very interesting properties. One is that it has a higher degree of fault tolerance than Web 2. And the other one is that you no longer need to place trust in a single entity running the whole show. So in Web 3, what you have is a network of nodes, and they independently operate, they run the same protocol, and there is no leader in this network. So there's no one calling the shots. And therefore it becomes really hard for any given node to gain sufficient power to tamper with the provisioning of your service, or to violate the integrity of your data, or to corrupt the system in any way or form. So Web3 is really a very good candidate to power what's coming next in this 21st century. Now, the thing is that most Web3 implementations, they use blockchains, but a type of blockchain that is public. So in a sense, they have given up on this key ingredient, confidentiality, that we argue was a catalyst for the growth of Web 2. And this may explain why, although Web 3 is thriving, it actually hasn't reached the size that Web 2 has, because it's limited to applications that avoid confidentiality. Digital money and digital assets is one of those, but very soon you find the need to deal with confidentiality. And so this creates like a huge space of opportunity. at the intersection between confidentiality and decentralization. And that is precisely where Nillion is. We call it the Nilverse. So I'm going to be talking next about Web3 and in its both flavors, the blockchain flavor and the Nillion flavor. And I'm going to be talking about similarities and differences between the two of them. But maybe before I do that, it would be a good idea to dive a little bit deeper into what decentralization actually means. Vitalik put it very clearly in this graph. He talks about 3 different dimensions, which are orthogonal, that describe the degree to which a system is decentralized. There is the architectural side of it, the political side of it, and the logical side of it. The architectural is about how many physical computers do you have, but it's also about the mathematics and the protocol running inside of those computers and the guarantees that they provide in terms of how many faults are they able to cope with without, interrupting the service from the network. So it's about Byzantine fault tolerance, maths, and protocols. Political is more complex because it's about how many individuals or organizations are actually controlling those computers. Ideally, we would want to see a 1-to-1 ratio. And it's also about who is making those decisions, the critical decisions that govern the network. So it's about protocols again and mathematics, but it's also about governance. It's about economics because you want to be creating the right incentives to, to make the nodes only run. So the entities only run one node and nothing more. So you want to prevent civil attacks. And also it's about legal, because you want to be creating the right legal structures that guarantee that the assets will be managed in a decentralized way and the decisions will be made in a decentralized way. Blockchains have these 2 dimensions, but they don't have the 3rd dimension, which is the logical decentralization. This is about how many, whether you can divide the operations of your system into subsystems. So is your system something that is unique, that, keeps the integrity of one thing, or can you kind of slice it in several pieces and still those pieces would operate? In a blockchain, as I said, this is not the case. If you slice the blockchain in 2, then you kind of defeat its purpose, which is to keep the integrity of a single thing that is a ledger, a global ledger. So if you slice it in 2, you will have 2 versions of that ledger, and then you no longer have a properly functioning blockchain. However, in Nillion, this is not the case, because you can have clusters, you can have pools of nodes, and there is a high degree of decoupling between those pools of nodes. They don't need to collaborate to create a global agreement on some superstructure like a ledger. There's nothing like that, but rather those clusters operate independently, receiving requests for computations, delivering on those computations, and producing results. And that's it. And that's why the playground for Nillion is that of a 3D scenario, whereas that from blockchain is a 2D one. So just looking at these 2 pictures, you can already sense that we're talking about a different flavor of decentralization with Nillion. And so the rest of the presentation, the narrative is going to be around comparing blockchains and NMC, which is the underlying cryptography for Nillion, in different aspects. So we're going to be talking about the purpose, the storage model, and also the computational model. Beginning with the purpose, obviously, the purpose of blockchains is very different from that of Nillion. Blockchains were made to manage digital assets, and so they're very good at creating this public ledger that is immutable. But Nillion was created with an entirely different purpose in mind, which was to provide secure storage and compute capabilities. So we're talking about something else. We don't really need to keep track of a global ledger. And as we will see, that has tremendous implications in terms of technical decisions being made, but also in terms of performance. The second dimension is storage model. And as I said, essentially what a blockchain is a huge ledger, and you get consensus on the value of the transactions on that ledger, the order of those transactions, which is equally important. This ledger is typically mutable because that provides guarantees that assets are not being tampered with. And it's also typically public. At least it is verifiable in some way or form. And in Nillion, what you have is you can think of it as records. So you have records like you would have in a database, and you could add access control structure to those records. You can make them maybe constant so that you cannot change them, but typically you will want to change them. You will want to make them public sometimes. So sometimes you will have public variables, but sometimes not. Sometimes they will be private. And so it's a much more flexible storage model in that sense. These two slides that are coming next, I'm going to go a little bit faster because they touch on a little bit on the maths, which will be covered in the other video. But nevertheless, we need to meet the two protagonists of Nillion, which are the blinding exponents and the particles. So in typical SMPC networks, what you do is that you hide the secret inside of a polynomial. So, and then what you give is shares of that polynomial, which are evaluations taken at different points in the polynomial to the different nodes in the network, so that no single node has enough information to reconstruct the secret. They need to gather enough shares, enough evaluations to be able to interpolate the polynomial and reconstruct the secret. In Nillion, we take a slightly different approach. Instead of using this primitive of the polynomials to hide information, we use something else. We turn the secret into a particle. You can think of a particle as kind of an encrypted version of the secret, but it's not like the conventional encryption, because this one is ITS, and I'll talk about that in a minute. So it's a very powerful encryption form, let's call it like that. And the blinding exponents, they are like the keys. So you're putting the secret in a box, which is the particle, and you're locking it with the blinding exponent, which is the key. So the question is, the keys are the sensitive part here, right? So what we do next is to put the key inside the polynomial. So instead of putting the secret in the polynomial, we put the key. And then we provide shares of that key, which is the blinding exponent, to the different nodes in the network. So for us, a secret is represented as particles and shares of blinding exponents. Particles are ITS. Now, what is all this fuss about ITS? It's called information theoretic security, and it's the golden standard in cryptography because it guarantees security even in the presence of computationally unbounded adversaries. And it may be interesting as well for those use cases that have to do with regulatory compliance, because only in ITS security can you prove that you're not leaking information at all. In fact, that equation that you have up there with the particles, what it says is precisely that if you are shown a particle, P, hiding a secret, S, you don't learn anything about the distribution of secrets. Therefore, the particle doesn't contain any information. Now, the next question is the blinding exponents, which, if you remember, were like the key that opens the particle. So we better keep them safe. We put them inside of the polynomial, and polynomials also are ITS. This time, it means something slightly different. It means that if you're working with a polynomial of degree t, and you get t plus 1 or less shares, sorry, t or less shares, those will be completely independent and uniformly random, which means that they don't contain information. Only when you get the t plus 1 share or more are you then able to reconstruct the blinding exponent. And we want that mechanism to be in place because we want this process of storing information to be reversible. We want to retrieve it as well. So that would work with working with more than t plus 1. So a big question then is, how big is t? Because it plays an important role in the security of the system. Luckily, t is a parameter. You can play around with it. You can increase the number of nodes, you increase t, essentially. But even for those applications that are very sensitive, there are ways of going beyond this level of security using homomorphic encryption. You can homomorphically encrypt the shares, And therefore, it wouldn't even be enough to gather enough shares from the blinding exponents. You would also have to break encryption. So it's like a two-layer possibility that we have here for those cases that require an extra mile in terms of security. Now, I said that we have particles and shares because particles are ITS. We don't really care about what we do with them. We could store them in a centralized database. We could store them in the client. We could store them in the network itself. What is really sensitive is what is it that we do with the shares of the blinding exponents. We're not storing the blinding exponents. That would be a centralized key store like LastPass. What we're doing is we're breaking those blinding exponents into a puzzle of pieces that reveal nothing unless you gather enough of them. And then we're sending those to different nodes in the network. So we're talking about the decentralized key store. And by decentralized, I mean that you enjoy all the nice properties of decentralized networks. You have fault tolerance against Byzantine faults, you have attack resistance, and you have collusion resistance. Now let's turn to the computation model, which is where things get really interesting. One way of looking at this is comparing the whole end-to-end flow from a blockchain and from a Nillion computation. And of course, in a blockchain, you start with a transaction, you have a smart contract, you want to be running that smart contract. So you send the transaction, it hits the mempool, then it has to wait there till a node includes it in a block that it's preparing. It's going to be running that smart contract locally. Then you have to wait for global consensus to take place and a consensus that chooses a block where your transaction was in it. And then typically, if you don't have instant finality, you will have to wait for a number of blocks to get enough probability that the transaction has been successfully accepted. And then you have the process of reading that the result from that smart contract. So in Nillion, let's do this experiment. In Nillion, at first sight, it would look like this is very similar. And my purpose in the next, with the next slides, and I will be showing this slide again at the end, is to change your mind about that, to really explain that when we look at the different steps, we're talking about very different things, in fact. And so in Nillion, yeah, at this level, superficial level, okay, we're starting with a new computation, it gets assigned to a cluster, computation runs, and then you have the same operation where someone reads the result from the computation. But let's now take a deeper dive into each one of these steps and compare them. And hopefully I will be able to convince you that actually they're very, very different. Starting with the first one, transactions are typically user originated in a blockchain, but the inputs to a computation in Nillion can come from users, but they could also be previously stored in the network, or they could come from another computation. So in a sense, you have more flexibility here. Regarding the second step, one way to think about what's going on in a blockchain is to think in terms of queuing theory. So you have this buffer, which is the mempool, transactions arrive, and then the whole network operates as fast as it is capable of producing blocks. So you can model it with a single server, a server that all it does is take transactions and put them in blocks. And the time it takes to do that is the time it takes for the network to reach consensus. So the system behaves as a single computer. We're touching upon the same concept of logical decentralization that we mentioned before. Because of this, you cannot slice it into halves. It operates as a single whole, as a monolithic thing, and consensus is both on the value and on the order, and it's global. It is consensus on this global object that is the ledger. In Nillion, you have something very different because the system behaves as multiple computers, each computer being a different cluster. As you hit the queue with a computation request, it will get assigned to an available cluster. And that cluster will operate pretty independently from the rest of the clusters. They don't need to talk to each other to reach any type of global consensus or agreement on anything. So indeed, we're talking about a parallel system. And then consensus is, again, something that is not global. It pertains just to the result from that computation. And to understand the consequences of this, I've gone a little bit further with this queuing theory analogy and actually run some numbers. So this is the most simple model that you can find in queuing theory. It's called the NMC. The two first stems stand for memoryless because the interarrival process for the Poisson distribution is exponential, and also the service times are exponential. So let's forget about that for a minute. We're not going to get exact results. We're interested more in the qualitative reading of this. And what we care about is C, which is the number of servers that you have in your system. So in a blockchain, you would have C equal 1, and in Nillion, you would have C equal as many clusters as you have. Running some numbers and computing the average waiting time, which is this equation on the top, one notices that there is this factorial element in the denominator, and that has an important impact in performance, because this grows very fast, very easily. And so it makes WQ, the waiting time in average, to go down very fast as C, the number of nodes in your parallel system, increases. So the blue curve is a blockchain. It has only one. And already for 3 different clusters, you can see a lot of improvement in terms of performance. So beyond the numbers, as I said, we just don't care about them. The interesting result here is that as you throw more nodes at the network and you're able to build more clusters, actually performance increases. This is not the case necessarily for a network which maintains a single state. The more nodes you throw at it, the more communication those nodes will have to exchange. And then you will have to resort to layer 2 solutions and things like that. But at the very core level, here we're talking about a mechanism that provides scalability as you add more nodes to the network, which is, I think, an important difference in terms of performance. Now, coming to the next block, which is about the computations themselves, there are important differences as well. The first one that hits my mind is that smart contracts are limited in a blockchain because they have to follow this agenda from the block making paradigm. So they have to fit in a block. In Nillion, we're free from this paradigm. There is no block, there is no chain. Computation is a computation. If you're able to pay for it, it can virtually have any size. There's no limit on that. And also, as I said before, smart contracts are typically run as public entities. And so you can read all the inputs, outputs, and internal variables. Whereas in Nillion, we have this continuous balance between private and public information. You can have public variables, but also private ones. And conditionals, I think, illustrate this balance between privacy and performance, because by definition, when you try and compute a comparison, you want to extract some information from the variables that comprise or that take part in that comparison. But that goes against the very same, the reason why we are hiding information. If you're good at hiding information, then you're bad at running comparisons, and vice versa. So here you have an inherent trade-off that you can kind of address in 2 different ways, at least. The first one is, if you lean on the security side, then you would evaluate all the branches in the program, and that would be ITS, and then you would just be revealing the right branch at the result, the right result that covered the right track of branches. But if you want to get some more speed, then you would be leaking some information with every conditional, and in doing so, you would be saving the effort of running extra branches in the program. So this is a very good example that privacy in Nillion is something that you can play around with, is dynamic, and you can always find a good trade-off for your given application. Now, let's talk a little bit about the underlying cryptographic primitives, NMC and ZKP. Blockchains, I said before that most of them are public, but there are some which are not public, like Mina or like Monero or Zcash, and they typically all make use of zero-knowledge proofs. Now, zero-knowledge proofs are to blockchain what NMC is to Nillion, and it's not like one is better than the other one. They serve different purposes. So what I'm showing here on this slide is what would happen if we tried to use ZKP for the purposes of Nillion, of building a decentralized compute engine. And as well as ZKP fits in with blockchain, we will see that is not the case with what we are building, which is a decentralized compute engine. The first difference is that in ZKP, the prover needs to see plain text inputs. And that is okay if all I want to do is maybe prove that my balance is consistent, but it's not okay if I want to mix information from several sources, because then the problem is who is going to see that information, who is going to become the prover and get access to those inputs in plain text. In NMC, we don't have such choice or conundrum, because in fact, no one sees those inputs. So it is okay to compute on inputs coming from one source or from 10. The other thing is that ZKP is really not meant for storage and retrieval of information. You generate a proof that outputs a Boolean number. It's a 0 or 1, it's true or false, but you cannot retrieve from that proof any information. It's really not the purpose of a zero-knowledge proof. Whereas the purpose of Nillion and MPC in general is to do that, precisely that. So it becomes like the right primitive to build a compute engine on top of. The other two differences are more technical. Typically, for blockchains, the zero-knowledge proofs that are used haven't been proven in the UC framework, which is a framework that enables you to compose protocols and yet guarantee that they're still safe. So that is very important for Nillion. We want to be able to compose things because we want to create a marketplace with different libraries, different programs, and be able to freely combine them without exposing the security of the system. All the proofs in NMC are done with in this UC framework, and so you can compose everything that comes out of them. And the other thing is that also typically, not always, but typically, most blockchains make use of non-quantum secure cryptography, where NMC by default is making use of quantum secure cryptography, but we do not discard the use of non-ITS cryptography in the future. We leave that door open again for reasons of trade-offs between performance and security. And so we come to the final step, which is very interesting. It's about the way the two networks arrive at consensus to an agreement on what they do, which is compute, or in this case, in the case of blockchain, a ledger. Here we have like the four steps, the four final steps to a computation in a blockchain case on the left and in Nillion on the right. So you need to reach this global consensus, which requires the nodes to exchange messages in a blockchain. And then if you don't have instant finality, then you need to wait for a number of blocks. And then the assumption that we're making here is that we are an external node, which has not participated nor has witnessed consensus, and therefore is coming like fresh from the outside world and wants to see what is the result from that computation. In these circumstances, if you don't trust any node in the network, you would have to read information like the last block from the chain from different nodes and compare those, because the nodes could be lying to you, could be cheating and giving you a wrong version of that block. So, and then you would run like a local comparison of those blocks, and which looks like a local consensus. If all of them are the same, then you're fine. If some of them are different, then you would pick up the most frequent version. In NMC, you don't have the first two steps. You don't have anything related or close to a global consensus. And also, therefore, you don't have finality issues. But the other two steps are similar, because when the computation has finished, every node ends up with a share of the result. And you want to be reading or receiving those shares as the external nodes so that you can reconstruct the result from the computation. But the thing here, the tricky thing is that those shares are not the same by definition. They're evaluations of a polynomial. And for the local kind of consensus that we were running on the blockchain, we were relying on that assumption that the blocks would be the same, and if they're not the same, someone is cheating. But here, by default, whether they cheat or not, there will be different. So how can you tell? How can you tell the difference whether a node is giving you the right share or is cheating and giving you something else? This is where something called error correction codes come to play. They come from information theory, and they have been used already in other MPC protocols. The idea is that you add some redundancy to the shares. So if you're working with a degree T polynomial, which means that T plus 1 shares are enough to reconstruct the polynomial, you would be adding more shares of that same polynomial, 2T more shares, so that in total you have 3T plus 1. And now imagine in your head that you get all these shares, 3T plus 1, from the different nodes. And you build with these shares a point, a multi-dimensional point on an n-dimensional space. So every one of those shares is a coordinate. The thing is that those coordinates are not going to take all the n-dimensional space. They're going to be on a lattice of equally spaced points. And the reason is because once you've defined the first T plus 1 shares, which characterize the polynomial, the other 2T shares are not random. They have to lie on the polynomial. And therefore, not every single point possible in this space is actually corresponding to a viable polynomial of degree T. So you can play around with this. And if when you get a vector of shares that you read from the nodes in the network, they correspond to a point on the lattice, then you know for sure that everything is fine, no one has cheated, and you have received proper shares. But if you get something else, like this red spot, which is slightly off the grid, then you know for sure that someone has cheated. And moreover, you can also, since you can compute distances, compute the distance to the closest point on the grid and use that as the set of points that you can reconstruct the polynomial from. So you can still correct and reconstruct the secret as long as the number of parties cheating has been less than T plus 1. And so it is very interesting because you can not only identify that there's something wrong, but actually also know which nodes have cheated and take proper action, and actually correct up to a certain number of wrong shares the result from the computation. So this is the core mechanism that allows NMC to provide Byzantine fault tolerance. And as you can see, it's a mechanism that runs locally in a node. So in a sense, like in the last step of the blockchain, this consensus in Nillion is something local. And one way to think about it is in terms of classical versus quantum mechanics. Blockchain is like a classical system. At every point in time, you know everything about the system. You know the state of the ledger, in other words. But with Nillion, this is not the case. The state of the system is probabilistic. You know nothing about it. It's hidden. So it's like a quantum system governed by a wave function. And it's only when you measure some aspect of this system that the wave function collapses and provides you with a result. And the equivalent in Nillion is it's only when you measure a result from a computation can you then obtain that result in a consistent way, so running this local consensus, but the rest of the network still remains unknown. It's still fuzzy. So this is the one way of thinking about consensus in Nillion compared to consensus in a blockchain. So I hope, coming back to this first slide, that now you have some more color to each one of these steps, and it becomes clear that these two animals are completely different. The way they work, the way they operate, although they may look the same and similar at this level, actually when you dive deeper, they have very different behavior, and they constitute two different ways of achieving decentralization, in fact. So as takeaways, I would suggest the first one is Nillion is not a blockchain, that's for sure. So we have now two approaches to decentralization, which can be combined. They can even be complementary. For example, the Nillion token will be using a blockchain, but also Nillion can be used as a layer 2 or as an interoperability solution for blockchains. But also Nillion can go beyond blockchains and provide other solutions to other use cases. Decentralization, the flavor of it is different because in Nillion is the 3-dimensional version of it, and in blockchains is the bidimensional version. The purpose was different, storage was different, confidentiality was an element that was very important in Nillion. Also, the notion of having an access control in place and of having this decentralized key store with the error correction that provides this Byzantine fault tolerance, and the computation as well. Computations are confidential, so you don't need to open the inputs and see them to be able to compute on them. It has an input compute model. It allows for parallel compute when you work with clusters, and it breaks this curse of adding more nodes mean slowing down the network. And it also has this notion of consensus that is only local to what matters to you. You don't need to wait for consensus of a whole entity, a whole ledger that spans across the whole network history, but you're just getting consensus for what matters to you, which is your computation. It's something local, and therefore it's something scalable. So this is it. I hope you enjoyed the presentation. Thank you very much for watching, and see you next time.